All right, so now that we've talked about the electric field, we're going to bring in a new topic which is related to electric potential energy and electric potential. So the forces and the field together work to describe like acceleration, force, and so forth. When we did 1401, that's where you started. You did some kinematics and then you did some forces. After that, you moved on to energy. And that's where we're going now as well. So we're going to be shifting over from kind of a force perspective to an energy perspective. So we're going to be using kind of gravitational potential energy as an analogy because it's a little more complicated because we can have positive and negative charges, whereas gravitational potential energy just has mass, and mass can't be positive or negative. The gravitational force is always attractive. The electric force can be attractive or repulsive. But we did start with a definition of work. And the idea is that work is being done by the gravitational field to create the potential energy. And work is dependent only on the starting and ending points as long as you have a conservative force. So if you were to lift an object, say this mass M, this box, from point A to point B, and you would go direct, there would be some amount of work that would be required to be done. And if I was to then take this wibbly wobbly path over here and also lift the object to B, but in a slightly different situation, the work done is actually the same in both cases because work is based on the component of the force that's parallel to the displacement, or the force that times the displacement that's parallel to the force, which is actually the easier way to look at this. So in both cases, gravity is pulling down. So the only part of the displacement that we have to care about is this vertical displacement, which is just the height. So no matter which path you take, you're going to create an mgh's worth of energy by doing that. So the same thing is going to work with our charged particles because we're going to find that the Coulomb's force is also conservative. It does not matter what path we take. We just care about the starting and ending points. So if we look at the work done by a uniform electric field, so remember that uniform electric field is uniform in magnitude and direction, so you can picture it being created by a parallel plate. We'd have like a positive parallel plate and a negative parallel plate there, creating that uniform electric field. I have a test charge, Q0, that is placed into that field at some particular location, and my plates are separated by a distance of d. So the force on that charge is Q0 times E. The direction of the force is dependent on the charge. So if this is an electron, my force is up. If this is a proton, then my force would be down because protons feel the electric force in the same direction as the electric field. Electrons experience a force in the opposite direction of the electric field. The work done is independent of the path taken because the electric force is a conservative force. Yay! It so happened that work is equal to change in kinetic energy. So our conservation of energy then says because this is a conservative force, our change in kinetic energy is equal to negative the change in potential energy. This is our work energy theorem. This is conservation of energy. So we're kind of combining those two together to create that statement. So the work is going to be done by the component of the force that is parallel to the displacement. So we're looking for FD. So since we're just going from A to B or B to A, or this case, sorry, we're going from A to B, want the work done from A to B, we just need F times D. There's no angles or anything we need to worry about that. So our force is equal to Q0 times E. This is coming from the fact that our electric field is our electric force divided by Q0. We just rearranged that. And we're going to substitute that in for the force. So we get the work from A to B is equal to Q0 E times D. Okay, E is our electric field, D is the separation distance between the plates. Q0 is the charge of whatever particle we've placed into that field. Now, that work causes changes in potential energy. So our work is our negative change in potential, because when we come back over here, remember that our work is equal to our change in kinetic. Our change in kinetic is the opposite of whatever change in potential is. That's why there's a negative there. So that means if we rearrange and solve this, our change in potential energy is equal to negative the work from A to B. So I'm just going to add that negative sign in there. That negative sign is important. So our change in potential energy is equal to negative Q0 ED. Okay, but I don't want to know what the change in potential energy is. I want to know what the actual potential energy is at any one point. So our change in potential energy is equal to negative Q0 E times D. A positive test charge would therefore lose potential energy when moving from A to B, because our positive test charge is positive. So if we go from A to B, we're going to get a negative change in potential energy. So if you think what's happening, we've got this positive plate up here, negative plate. If I put a positive charge up there and I'm holding it in place, I am going to have to forcibly hold it there, because the repulsion force is going to be very, very, very strong. So that is going to create a lot of potential for motion. If I were to let go, that proton would then explode essentially out away from that plate and start accelerating. So I'm creating this big amount of potential energy. But as that potential moves, this particle is going to lose potential and gain kinetic and speed up, so that when it's at the bottom, it doesn't want to go anywhere. It's just going to stay there. That's going to be low potential energy. So our positive charge is going to lose potential energy from moving from A to B. Now, on the other hand, that negative test charge is going to gain potential energy. And it's going to gain that potential energy because when it starts off at A, it's already at low potential, okay? It doesn't want to go anywhere. It's already attracted to the positive charge. It's up there. So if you want to move it from A to B, you are going to have to do work and force it away from the positive charges and towards that repulsion of the negative charges. It does not want to go that direction naturally. So it is going to gain potential energy if you move it from A to B, and you're going to have to do work to give it that potential energy. So parallel plates are pretty easy. When we look at point charge, it's a little more complicated, because we know that the electric field gets weaker the further we go, because our electric field is kq over r squared, so the further away you go, the much weaker the field. So this is going to be a little more complicated. So let's assume that we have a test charge Q0 and our source charge Q right here. Really, it doesn't really matter which one is the source, but the bigger one they've shown here is our Q. They're separated by a distance of r. So at that one particular instant, there is a force equal to Q0 over r squared. The force between the two charges, that's our Coulomb's law. We have to displace our charge Q0 along a radial line from A to B. We'll see that that radial line doesn't matter. We can actually take any wibbly-wobbly path to get there. But if that's what we're doing, then what's going to happen is our force is going to get smaller. Now, work we could not solve without calculus if our force is changing. Okay, that was one thing. You have to have calculus to deal with that. But what's fortunate is we don't need the calculus, because we know that our force is conservative. So we only care about those fields. But if you did the calculus, the path would not be dependent, because we would only care about the portion of the force that's parallel to the displacement. So all of the side-to-side motion wouldn't matter. All that would matter are the parts that are actually parallel to that electric field, because the path is conservative. So if you were to do all the calculus and walk through the steps we did for the parallel plates, which we could do without calculus, what we would find is our electric potential energy is going to be Q0 over R. So we have an inverse relationship instead of an inverse square because our electric force is KQQ0 over R squared. Okay? And what's going to happen, though, is going to be different depending on whether we have like charges or opposite charges. Gravitational potential energy was a little less complicated because our mass cannot be positive or negative. So what ends up happening is that if we look at the separation distance, so this is this is a separation distance of 0, so that's the particles exactly on top of each other, that would give you an infinite amount of potential energy, either positive potential infinite or a negative infinite. So as you get further away, the potential energy goes towards 0. So that's true no matter what your charges are. And that just kind of makes sense because our electric force is also getting closer to 0, so our potential energy is getting closer to 0. But if we have like charges, positive and positive or negative and negative, this is actually a decreasing amount of potential energy because when they're forced really, really close together, they're going to have a huge repulsive force and they're going to be pushing themselves apart. That's a big amount of potential energy. And so their potential energy is going to decrease to 0 because you're going to have a positive and a positive or a negative and a negative. Okay, your electric potential energy is always positive, and so it's going to decrease towards 0. Now, if you have opposite charges, if one of these is positive and negative, or it doesn't matter which one it is, the problem is your potential energy is going to be negative, and it's always negative. This is the one that acts like gravity. I don't know if you looked at universal gravitational potential energy in your 1401. UG is equal to negative G M1 M2 over R, and there's actually a negative there because your universal gravitational potential energy when you're looking at like planets and solar systems is always negative. So when they're really, really close together, you get very, very, very small negative, like very negative infinity is actually a tiny amount of potential energy. And what's actually happening is as they get further apart, we get an increasing amount of potential energy. So your opposite charges gain potential energy the further apart they go, because when you separate them, they want to come back together. So, and the opposite is happening if you have like charges. So that's what makes this a little bit more complicated than what you did with gravity. So the signs of the charges have to be included in the calculation. The potential energy is 0 when the two charges are infinitely separated. This is actually an assumption that has to be made in order to do the calculus. You could technically define 0 to be wherever you wanted. We do that when we do gravitational potential energy like on Earth, and I'm here. And I'd be like, oh, I'm going to assume that UG equals 0 at the surface of the Earth. Well, technically it's not. If you use this equation, it's not 0. But we assume it's true. So this equation assumes that our potential energy is 0 at infinity. So for example, we want to calculate the electric potential energy of a hydrogen atom. So we've already looked at a hydrogen atom a little bit. So we're going to use the fact that our U is going to be our K, Q, Q0 over R. It does not matter which is Q or Q0 in this case. And then because these are both elementary particles, I can actually just use E for the proton, positive E, and I could use a negative E for the electron over the separation distance R. So our U is going to be 9.0 times 10 to the 9th Newton meters squared per Coulomb squared for Coulomb's constant. Positive E, this is really going to be a negative, actually I simplify this down, this is going to be a negative K E squared over R. So that's going to be 1.6 times 10 to the negative 19th coulombs squared. And then their separation distance is 5.29 times 10 to the negative 11th meters. And when you go through and plug in, we get 4.355, so 5 So let's just do 3 sig figs, 4.36 times 10 to the negative 18th joules. And that should be negative. I need to make sure I got that negative there. So this is a negative potential energy because when we looked at that chart, when we have opposite charges, our potential energy is always going to be negative. We can never have a positive amount of potential energy. The biggest potential energy we can have is 0 for oppositely charged particles. So what we can do with energy is something that we couldn't actually do in a lot of situations before. I don't know if you noticed, but we did force calculations, acceleration and velocity calculations for a uniform field. We did not do any charged particle calculations when I have like, oh, a positive particle, a negative particle are at this location, release them, what's the force, what's the acceleration? The problem with that is we cannot do kinematics for point charges because the force isn't constant as the charges start to move. So we have to do energy. Okay, so that's why we're bringing up this type of problem now that we have energy that we can work with. So we have a charge positive 2q, has a mass of m, and is released from rest from a distance r from positive q. We want to know the velocity as it approaches r goes to infinity. So we're starting at this position, and we've got a positive q here, and we got a positive 2q, so they're going to be repelled. We are assuming that the positive q is being fixed in place. It doesn't specifically say that, but that's what's being implied. So that this guy is going to get accelerated away, and we want to figure out when r is infinity, how fast is it moving? We do have to assume that it's fixed in place, otherwise it would get very complicated because they're both moving and the distances. Oof, we don't want to do that. So, whenever you do a situation like this, when you're doing energy, you always want to consider your two positions. So our first position here, and our second position is here. So at this position, we are going to definitely start with some potential energy. Oops. Okay. And that is going to be our K Q0. They're both positive, so don't need to worry about that, over r squared. And our kinetic energy at the start is 0. So we are going to then go out when our potential energy is at r equals infinity. So remember, we defined our potential energy so that it's actually 0 to infinity. So we picked r equals infinity so that we don't have any potential energy. But if we weren't at r equals infinity, you just use another Q0 over r squared calculation. And so what we want to do is we want to find our kinetic energy at this point, so that way we can find our speed VF at position 2. So I would always start off by a statement of conservation of energy. So I would say K1 plus U1 is equal to K2 plus U2. And then what you're going to do is you are going to sub in the zeros. So K1 is 0, U2 is 0. So that gives us our U1, which is equal to KQ times 2Q over r squared is equal to K2, which is going to be 1/2 mVF squared. So we're looking for our VF. So what I can do is I can multiply by 2 over m. The 2's cancel, the m's cancel. Do that on both sides. So we get, I can simplify this to 4KQQ over m r squared is equal to VF squared, and then take the square root of both sides. So the VF squared cancels, so we end up with VF is equal to 4K big Q little q over m r squared to the square root. You can simplify that down a little, but that's fine. At this point, if it gave you numbers, you could just sub in the numbers. Okay. Okay, that gives us the ability to calculate a speed. So we could not use forces and kinematics to do this because our acceleration is not constant, so our kinematic equations are not valid in this situation. So electric potential is a little bit different. So it's kind of like the relationship between electric force and electric field. So we had that our electric field was equal to the electric force divided by Q0. The whole point was to eliminate the need for a test charge, a second charge. All we wanted to worry about was the source charge. So the same thing is going to be true here. So our electric potential, which we're given the symbol capital V, is essentially the electric potential energy we would have if we had a test charge Q0 there. So the relationship is similar. So we're basically dividing Q0 out of the calculation. So we end up with V is equal to U over Q0, or U is equal to Q0 times V, if we wanted to write it the other way. So electric potential has units of volts. Now this is one of those weird situations where the unit and the symbol are the same. So we use a capital V for electric potential, and we use a capital V for the unit of volts. And a volt is the same thing as energy per unit charge, U over Q. So that's the same thing as a joules per coulomb. So 1 volt is the same thing as 1 joule per coulomb, in case you see it. Now, electric potential is not a vector because electric potential energy is not a vector. So actually, you'll find that you probably like working with electric potential a little better than you like working with electric field or electric force, because you don't have to do any pesky vector addition. So now we can use this relationship between the electric potential and the electric potential energy to find the potential at different points. So, for example, we have this parallel plate. We found that the change in potential energy as we go from A to B was delta U equals negative Q0E times D. Now, we said that U divided by Q0 was equal to V. Well, the same thing is going to be kind of true in the fact that delta V is going to be delta U over Q0. Because a lot of times we're dealing with potential and potential energy. We don't know the actual values. We just care about the difference. How did it change? Because what's the change in potential energy? Because that can give you the change in kinetic energy. We don't really care what the actual values are, just the difference between points. So what this tells me is if I wanted to find the potential difference, and by the way, this potential difference is voltage. When we talk about voltage later, this delta V is going to be delta U over Q0. Well, for parallel plates, that delta U is going to be negative Q0E times D divided by our Q0. So the Q0 is going to get canceled out here. Kind of like what it did when we did the electric field versus Coulomb's law. So this gives us that our delta V is equal to negative E times D. Now, why is there a negative here? So there's a negative here because as our electric field increases, our potential is going to decrease. So if I go from my electric field here, my electric field is going to decrease. So this is low potential, and this is high potential. So that's what that negative is. If I just wanted to find the potential difference, it's going to be the absolute value. Then it's just E times D. And then I don't really care about the negative. And when we talk about the absolute value here, that's really this potential difference is what we're talking about with voltage, and we don't really care which way the particles are moving. We just care about the difference in potential, because that's telling us how much our energy is changing between those plates. But that's why there is a negative here, because as we go from high voltage to low voltage, our decreasing potential, so our delta V has to be negative. Our direction of our electric field the opposite happens to our delta V. So that is an example there with the parallel plates. And like so, we're usually caring more about the change in potential between the 2 points, not the potential at any one particular location. Now, what about if we have this point source, the electric potential at a distance r from a point source? So this one's a little more complicated. We know some things about this point source. We know that the electric field is equal to kq over r squared. We know that the force, if I was to put a test charge here, q0 at somewhere, at that radius of r that's in that equation, the force would equal k q0 over r squared. So you're just adding that in. We earlier showed that the potential is going to be k q0 over r. Actually, I think we used a lowercase q at that point. Okay, so these could be lowercase q's. We just had used a capital Q earlier for that. Okay, so that lowercase q. But that's different than our test charge q0. So there's a pattern, and the pattern of this is based on the fact that to get between force and potential energy, there's actually a calculus relationship based on taking an integral or a derivative. But the big thing is as you go from force, which is our action at a distance, to our energy view, our power of r decreased by 1. That's the only thing that happened. So what ends up happening is your potential is also going to be similar. It's going to be kq over r. I could use Gauss's law to prove this. I could use a lot of calculus to prove this. But when you're looking at point charges, this is what's interesting. When we're looking at the left side of this is only looking at the source. Okay, so we can find the electric field that is being generated by this source charge. We can find the potential at any point. We're going to talk about equipotential surfaces in a little bit. So if I'm at a particular radius of r, the v at that point is going to be constant at that radius of r. That's all dependent on the source. When we look at force and potential energy, force is a vector, potential energy is not. Electric field's a vector. Our electric potential is not. It requires the interaction between the source and the test charge. But the pattern is similar because electric field and electric force are two different perspectives, two different ways to analyze the field. And then the electric potential and the electric potential energy are two ways to kind of examine that. And the whole way you go back and forth between those is just the fact that when we go here, our electric field is our force over our test charge, and our electric potential is our potential energy divided by our test charge. So we can eliminate out that test charge and we can go this direction, okay? We can go from our force to electric field. If I want to go the opposite way, if I have an electric field and I have a force, I could just multiply. So I can go the opposite direction. If I have a field, I want to find the force, my force is going to be Q0 times E. If I'm going from my potential to my potential energy is going to be Q0 times V. So those are really handy relationships that we can use to kind of establish some relationships between these. Because the two most common charge distributions that you are going to see in this class are going to be the parallel plates and the point charges. So we do have to be careful with symbols. So we have capital V is the symbol for electric potential. Capital V is the symbol for the volt. Lowercase v is the symbol for velocity or speed. So you have to be careful, okay? You need to work. I've seen people cancel out wrong V's and the V's that don't match, and chaos can ensue. Thank you, physics, for making things so much easier for us. So just make sure, especially if you're using some sort of conservation of energy problem in which you're dealing with potential energy, and speed and velocity, that you're very, very careful. So some things that are true for whether you have a positive or a negative charge. Potential increases if you move in the direction opposite to the field. So if I have an electric field going this way, if I move, no matter whether I have a positive or a negative charge, if I move that charge in the opposite direction of the field, V is going to increase. And so therefore, if I move in the same direction as the field, my V is going to decrease. So that is true whether you have a positive charge or a negative charge. So here's a little conceptual example. So we have points A, B, and C. And A and B are in the same horizontal distance. C is further to the right. We often talk about potential as a potential difference. Potential difference is going to be delta V. This delta V, by the way, is what we traditionally call voltage. Voltage is a delta V, not a V. If you took physics in high school, your teacher might have called V voltage. It's really delta V. Okay, that's going to be a little important, but not super important. So it's the difference in potential between 2 points. So here I want the points between A and B. So remember, delta is always end minus start. So we're ending at B and we're starting at A. So if we move from A to B, what happens to what's the difference in potential? Pause, think about it. When you're ready, hit play. So if we take a look at this example, we have not moved parallel to the electric field at all. We have moved perpendicular to the electric field. So our electric field points in the direction of decreasing potential, but since A and B are in the same relative horizontal position, we have not moved parallel to the field, so there is no, oh, that says on, sorry, there's no potential difference. So the correct answer is delta V AB equals 0. So if you move perpendicular to the field, there will never be any change in potential. All right, so here's a question. Point C is at a higher potential than A. True or false? Think about it. Hit pause. Think about it some more. Hit play when you're ready to go. So the electric field points in the direction of decreasing potential. So we are going to have lower potential here. We are going to have higher potential over here. So C is at a lower potential than point A. False. All right, here's another one. If a negative charge is moved from point A to point B, its electric potential energy increases. Pause, think about it, and then hit play. So, our potential energy is the product of the charge and the potential at that location. So, we know that U is equal to Q0 times V, because we define V as U over Q0. So if we go from A to B, well, our potential is not changing, so therefore our potential energy is not changing. So there is no potential energy change. So as long as we are moving perpendicular to the field, we have no change in electric potential, we have no change in potential energy, so it doesn't change. So here's a cool little analogy. So if you think of what's going on with kind of potential, this brings up the idea of equipotential surfaces. So we saw those before. When you had a positive charge, we had our electric field going away. And I showed you the equipotential lines. And they got further spaced out the further away you go. Picture these as a topographic map. If you have a topographic map, you might have like ridges, and this might be the top of a mountain, because this might be 500 meters, this might be 1,000 meters. So this is 1,500 meters. So that is showing you like a mountain peak. The same thing is happening here. So think positive charges are always going to be at the highest potential. Negative charges are going to be at the lowest potential. Think of the positive charges as a hill and the negative charges as like a well or like a valley. So the equipotential lines represent lines of equal potential. That's where V is constant, where our capital V is constant. That's where our equipotential lines are. And so with those, we can see that like for point 3 to 4, they're on the same potential line. So if I move from point 3 to 4, no work has to be done because there's no change in potential. However, if I move from point 1 to point 2, that if it's a positive charge that's moving, it's going to be attracted. That's almost like going downhill, okay? If this was a negative charge, if I wanted to try and force that negative charge in, okay, that would be like repelling, okay? So these would be really good ideas to kind of represent what would a positive test charge do? How would a positive test charge move? What happens to the energy? Well, the positive test charge is going to lose energy as it falls down that well, whereas a positive test charge that was going to go up that hill is going to gain. And then an electron is just going to do the opposite. It's kind of an analogy. It may work for some of you, may not work for others. So if you take this three-dimensional representation and project it onto a two-dimensional surface, this is exactly what this looks like. So what you end up having is you have your positive charge and your negative charge. You have your 0 volt line, which is where P1 is. 0 volts is going to be halfway in between. And then you can see that our potential goes up as you go this way. Our potential goes down as you go that way, with negative being lowest potential, positive being highest potential. So you can see that there's a relationship there. And then our electric field always has to go from positive to negative. And what we're going to find is that electric field always has to cross these potentials at 90 degrees in every case. And a charge can travel along any one of these lines and never lose potential energy. There'll never be any work being done. If released from rest, positive charges move towards the lower potential freely. Negative charges move towards the positive charge freely, and they will follow the paths of the field lines. So if we got a field line coming up here, coming down here, that's the path. So if I release a positive charge here, it's going to follow this field line here, and those field lines have to intersect at 90 degrees. I didn't quite get this one at 90 degrees, so those should always intersect the field lines at 90 degrees. So here's some more examples of those equipotential surfaces. So here's your surface for just a point charge. Here's two positive charges. And at all points, the electric field has to be perpendicular to the equipotential surface. So if you look at any of these intersections, if these are drawn correctly, they should be at 90 degrees. Doesn't look like all of these. So sometimes these pictures are drawn by artists, not physicists. But these should always intersect at 90 degrees. All right, so our kind of last topic here for this section is conductors in equilibrium. So one thing we talked about was that if you have two conductors and you touch them together, that the charges are going to move. This is our very first lesson. And the charges are going to move so that way the total charge remains the same. Now, if those two charges are on objects, conductors, that are exactly the same size and shape, they're going to redistribute themselves so that the charges are exactly equal. So if you take this positive Q and this negative 2Q, that adds up to a total of negative Q's worth of charge. So at the end, I'm also going to have a negative Q's worth of charge. So that when they separate, they're each going to have a negative half a Q's worth of charge. Okay, so I see how that works. Now, how about other situations? What about if they're not the same size? So they still have to redistribute themselves so they both end up negative. But if the objects have a different radius, what has to be true is that their potentials at their surface have to be the same. So what is going to be true is that V at the surface of the small sphere has to equal V at the surface of the large sphere. That has to be true. Well, how do we know what that V is? Well, we found with Gauss's law in the previous unit that our electric field was equal to kq over r squared. And we found that this was actually true for a point charge and we said that the electric field was equal to surface area over E naught for any conductor. So if we had a spherical conductor, our surface charge density sigma was equal to our total charge over our surface area. So that would be Q over 4 pi r squared. So if we plug that in, we get E is Q over 4 pi r squared over E naught, but that just gives you Q over 4 pi E naught r squared, and then the 1 over the 4 pi E naught r squared is equal to K Q over r squared. So that actually just tells us that this is the same thing for a point charge or a spherical conductor. So it doesn't even have to be a point charge. It's basically, if it's some sort of spherical object, our electric field is going to be kq over r squared. Okay, that's going to work. That's going to be really, really nice. So basically, this big sphere acts like a point charge as long as you're outside of its radius. Inside, there's no electric field because our conductors cannot have electric field inside of them. But outside, it works fine. So how does that relate to our electric field? Well, let me simplify this down a little bit. We know that E is equal to kq over r squared for the sphere. It's also the same for the point charge. Well, we've already found the potential energy of point charges. We found that for a point charge, our electric potential energy was equal to Q0 over R. We also know that we had our electric potential is equal to U over Q0. So here's what's kind of cool. We figured out that the electric field is the same for a point charge and for a spherical source, okay, charge. That's not exactly a point charge. This potential energy for two point charges comes from Coulomb's law and matches this electric field. I could do this better if I could teach you calculus. Okay, this will make a little bit more sense. I'm having to do a little hand waving here to make this work. So because this potential energy works with this electric field for point charges, what we can find is that this also works for spherical charges. So if we take our Q0 over R and divide it by Q0, we find that our potential is equal to kq over r for both a point charge and for a spherical charge. So the electric field of a point charge and a spherical charge is E equals kq over r squared. We've now found that our potential is equal to kq over r. So knowing that that's true, we can then actually use that information to find the charges that these two spheres end up with once they're brought together and then separated. All right, so here is a similar example to one that we had already worked in terms of using Coulomb's law. So we have a positive charge Q1 located at distance d along the y-axis from the origin, and now we just have a negative charge Q2 located on the x-axis a distance 2d away from Q1. We want to calculate the electric potential at the origin. So this is a little different than when we had before, because in the other one we had 3 charges. But I need to have nothing at the origin in this case, so I removed the charge that was located at the origin, because with our equation, V is equal to KQ over R, if I had that charge here at the origin, the distance would be 0, which would give me an infinite amount of potential, so that would not really be a good problem. So instead, we have nothing at the origin. So the other thing that's really nice about this problem is because potential is not a vector, I don't have to do vector addition. So if I want to find my potential at the origin, I just need to find the potential from charge 1 and add the potential from charge 2. So since I'm using point charges, I'm using the KQ over R. So V1 is going to be KQ1 over R1. V2 is KQ2 over R2. So really this is just plug and chug at this point. I think I had, in order to find this distance R2, since we've already done that triangle, you would use the Pythagorean theorem. It's the square root of 3 times d, but you do that by doing d squared plus x squared is equal to 2d squared. But you'd find that that side is equal to the square root of 3 times d. So that is going to be our R2. R1 is going to be d. And we've got our Q1 and our Q2. So V is going to be K. Q1 is a positive Q over R1, which is d, is going to equal K times negative 2Q. And it does matter. We do have to include the positives and negatives, even though it's not a vector. Whether the potential is positive or negative matters. Oh, it should be a plus sign. And then R2 is the square root of 3 times d. So if I wanted to simplify this down, I would get a common denominator by multiplying the square root of 3 on top and bottom. So V is going to equal the square root of 3 KQ minus 2 KQ over the square root of 3 times d. And that can be simplified down a little bit. I get square root of 3 minus 2 times KQ all over the square root of 3 times d. So it doesn't really simplify it down. You could have just left it unsimplified. Unless it's like a multiple choice question, then you might have to simplify it down in order to make your answer match the given answers. Or if it's a calculation problem, you just plug in numbers at this point and you have an answer. So much nicer not having to do X and Y components. But I have to caution you, now that you know that you can do this, if you're given a problem involving forces or the electric field, you do have to include vectors. So if this had asked us to calculate the electric field instead, you'd have to be careful because the electric field is a vector. So at this point right here, Q1 would be creating an electric field away from it. Oops. Sorry, I'm too close to the bottom. So it's trying to... Oh, all right, hold on. I'll just write that over here. All right, E1. And then Q2 would be creating an electric field that would be towards it. So that would be E2. So in this case, you would have to do vector addition because the net electric field would be the vector sum of those. So our net electric field would have to be there. So you would end up calculating E1 and E2. E is KQ over R squared. So still not that bad, much easier than a Coulomb's law calculation. And in order to find your net electric field, that would be the square root of E1 squared plus E2 squared. because they make a right triangle that you'd have to use the Pythagorean theorem to find. So it's a little more complicated when you're using force and electric field because of the vectors. With electric potential and electric potential energy, you do not have to do vector addition. All right, so now what we're going to do, we are going to assume that we have brought those two different size spheres together and that they have redistributed themselves so that the electric potential, V, is the same everywhere. Because that's what has to be true for conductors in equilibrium. Yes, the electric field is zero inside, but now on the surface, the V is constant everywhere along this conductor. So there's going to be different charges on each of these spheres in order to make that true. We're assuming that our electric potential is equal to KQ over R. We can see that if we need the same V on both, that the bigger the R, the bigger the Q is going to have to be to keep that V a constant value. So our small sphere has a V equals to KQ1 over R. Our large sphere is going to be V is equal to KQ2 over R. So we're going to set those equal to each other. So we get KQ1 over R is equal to KQ2 over 2R. We can simplify down. We can see that the K's are going to cancel, the R's are going to cancel, so I'm left with Q1 is equal to Q2 over 2. So I know that Q1 is going to have exactly half the charge of Q2. But I still have two unknowns here. But we have another equation. We still know that charge has to be conserved. So we know that the total amount of charge we had at the start has to be the same that we had at the end. So originally we had a negative Q. The smaller sphere had a positive Q. The larger sphere had a negative 2Q. So when you add those together, we know that we have to have a negative capital Q's worth of charge at the end. So we can then write another equation that says that Q1 plus Q2 still has to add up to negative Q. So then what we can do is we can take these two equations and put them together. So what do these new charges have to be? So we said that Q1 is going to be Q2 divided by 2, and Q1 plus Q2 has to add up to a negative Q. So what I can do is I can just take this guy right here and sub in. So I get that Q2 over 2 plus Q2 is equal to negative Q. So I can make a common denominator. There's different ways to do this. So I get Q2 plus 2Q, that's going to be 3Q2 over 2 is going to equal negative Q. So if I solve for Q2, Q2 has to equal a negative 2/3 of Q. I can then take that back in and plug it in over here. So Q1 has to equal Q2, which is a negative 2/3 Q over 2. What ends up happening is the 2 on top and bottom cancel. So Q1 must equal a negative 1/3 Q's worth of charge. So when they were the same size, the charge distributed equally so that they each had half. But now that Q2 is twice the size, it needs twice the total amount of charge. So it ends up with negative 2/3 Q's charge, and Q1 ends up with negative 1/3 Q. So the larger sphere has twice the charge, but the exact same potential.